Hello everyone. In this session, we are discussing the acidic nature of phenols and comparing the same with the acidic nature of alcohols. So, phenol is a resonance hybrid of the following structures, where in three of the resonating structures, oxygen has developed a certain positive charge. So, because of developing a partial positive charge due to resonance, oxygen has a great tendency to attract this shared pair of electrons towards itself. Of course, it is already electronegative. On top of it, it has got a partial positive charge. So, the tendency to attract this shared pair increases, weakens the bond, and allows for release of H plus ion from the phenolic entity, and thus showing its acidic character. But the explanation for acidic character of phenols doesn't stop here. So this is an equation which is indicating phenol in aqueous medium releasing a proton H plus and forming the phenoxide ion. The acidic character of phenol will be established once I establish that phenoxide ion has a better stabilization or has greater stability than phenol. That would indicate that the equilibrium of this process is moving in this direction, forward direction, and that phenoxide ion remains as phenoxide ion and H plus ions remain present in solution, and the presence of these H plus ions would be indicative of acidic strength of phenol. So now what we are going to study is how is the phenoxide ion stabilized or showing greater stability than phenol. So phenoxide ion is also resonance stabilized. It has five resonating structures. In these five resonating structures, oxygen has developed a certain negative charge here, and in the other three, the negative charge is delocalized over the ring. Now, because of delocalization of this negative, what is delocalization? Not remaining at one place but moving around the ring at different positions in the ring. So, because of movement of the negative charge on the ring, this H plus ion is not able to attack the negative charge very greatly or very easily. Why? Because the negative charge, had it been at one place, this H plus ion would have known where to hit it. But because the negative charge is traveling all over the ring, there is no focal point of negative charge available for the H plus to hit or attack the ring, and therefore the phenoxide ion acquires a greater level of stability. Why? Because H plus is not able to come back to its negative charge as easily. Another reason for better stabilization of the phenoxide ion is the absence of charge separation. Now, what does that mean? That means in the structures of phenol, you saw that there were two different charges, plus here, minus, plus, minus, plus, minus, plus, minus. This is known as charge separation, that is, availability or presence of two different charges on the same molecule. As a result, what's happening is that some attractive force exists between the plus and minus charges present on this molecule. And attractive force is energy, and so the energy content of the phenolic structure increases, making it a little less stable as compared to phenol, which does not have any charge separation. It has only one charge. So in terms of charge separation also, no charge separation here, therefore greater stability of the phenoxide ion. And as soon as the phenoxide ion has greater stability, H plus remains in solution. If H plus remains in solution, that means acidic character is indicated. So I have already discussed that phenol shows presence of charge separation, therefore at a higher energy level and therefore less stable. And because of the greater stability of the phenoxide ion, the equilibrium is shifting in this direction, allowing for the presence of the H plus ion, which is indicative of acidic character. A quick recap in terms of points. Why is phenol a relatively good acid? Because it should have how is that indicated? Presence of H plus. But how is that? That is established by establishing greater resonance stabilization of phenoxide ion as compared to that of phenol. And why is that? Because of charge separation. No charge separation, only minus charge, which is delocalized over the entire ring. Phenols are stronger acids than alcohols. Why? For that, we need to show that the phenoxide ion here and the alkoxide ion here, as compared to the whole entities from which they have evolved, that they are more stable, then equilibrium will shift in this direction. If it is less stable, equilibrium will shift in this direction. So let me compare the alkoxide ion and the phenoxide ion. Alkoxide ion shows no resonance stabilization. So, as compared to the phenoxide ion, it has lesser stability. Along with that, the alkoxide ion has an alkyl group which shows a plus I effect. What is plus I effect? Electron releasing effect. So, it's releasing electrons, the moving electrons towards oxygen, as a result of which oxygen, already negative, acquires a little greater electron density and becomes an area for easy attack for the H plus ion to hit it. When H plus ion has a greater tendency to come back, why? Because no resonance stabilization, because electron density increases due to plus I effect, the equilibrium moves in this direction and therefore this becomes more stable. On the contrary, if, as we just discussed, the phenoxide ion is much more stable than the phenolic entity. Why? More resonance stabilization. Why? No charge separation in the resonating structures here, and the only negative charge that is available is also delocalized over the entire ring. So H plus does not know where to hit the negative charge, and therefore phenoxide ion, being more stable as compared to the alkoxide ion, makes phenol a better acid than alcohols. In the next session, we'll be discussing the influence of substituents on the phenolic molecule. And till then, do remember to repeat, revise, and reinforce. Till then, thank you and God bless you all.